Okay, so hi everyone, I'm Sunaina. I'm assuming that you can hear me okay. If not, please send a message or something. Uh, so let me just introduce myself and also give a brief description of what I'm going to talk about today. So I'm a postdoc researcher at Microsoft Research in Bangalore, and I've been here since last year. So it's been just over a year since I joined. Prior to this, I did my master's and PhD at Carnegie Mellon, and this was on the PhD was on speech synthesis, text to speech systems, and before that, I also worked on intelligent tutoring systems for my master's. Prior to that, I actually worked for a year in a speech startup in Hyderabad, and before that, I did my engineering from NIT Surat in computer engineering. So I've really got into speech recognition only recently, and one of the things that I was really interested in, of course, while I was at CMU, the whole deep learning boom was happening. Um, but one of the things that was pretty fascinating was the way deep learning has taken over many fields, and speech recognition is one of those, which I'm sure all of you know that there were lots of articles and things like that on how great speech recognition is now, thanks to neural networks. So I was really interested in sort of tracing the history of this and seeing what happened and what were the major things that deep learning really did. And that's what I'm going to try and talk to you about. So I'm not going to go very deep, so pardon the pun, into any of the algorithms or the deep learning techniques. I know that you've already had some really great talks, like the CNN talk. I watched that. So I'm not going to do that in this talk. I'm going to talk much more from an application perspective. So I'm going to talk about what speech recognition is, and also what was done in the past, what the machine learning solutions were in the past, and then what happened when deep learning was introduced, how it came about, and so on. And sorry, I'm just going to mute my system a little. Yeah. So that's what I'm going to talk about. So I'm hoping to finish this fairly soon, not more than 30-40 minutes, and then I'd like to take questions for a few minutes after that. So we should be done by 10, hopefully. Okay, so let's get right in. So this is the outline. I'm going to talk about what speech recognition is, what the problem is, and I'll talk about what traditional approaches were pre-DNN. Then I'll talk about what deep learning did. And this is not comprehensive. It's just going to be, some things that I felt were pretty interesting, but I'm sure that I haven't covered the entire trajectory of what happened. And then I'll talk a little bit about what's happening right now and what the open problems are and what people are interested in working on. Again, this is very biased from my point of view, and I'll talk about what I'm really interested in. So what's speech recognition? Well, simply put, it's you have some speech and you want to try and produce text out of it. So you want to transcribe somebody speaking, or you want to read out something, or you want an intelligent system to be able to understand you. So you want to be able to recognize the user and then do something based on what they say. So the kind of speech that you're trying to recognize can be of various types depending on the application. One of them could be read speech. So suppose your application is producing transcripts under, say, newsreader or some other kind of reading, then that kind of speech is read speech. The other kind could be conversational speech. So people having a conversation, you want to actually recognize. You maybe want to spy on people. Speech could be of various kinds. So it could be in a quiet room, quiet environment, or it could be in a noisy environment. So there's lots of background noise and other things that you have to take care of. There could also be various linguistic issues, like there could be different dialects. Even if you are recognizing in a single language, there may be dialectal issues and so on, which you haven't considered, or a user from, who uses a slightly different dialect, and you want to try and recognize that person's speech as well. So there are a lot of other conditions also, but these are some of the interesting ones. And of course, as I said, there are lots of applications for speech recognition. So, you have voice assistants like Cortana and Siri and so on. Medical transcription is another big thing in which speech recognition is used these days. So, you want to transcribe what the doctor is saying. You don't want a human to do that, so you have a machine to do that. There's another really nice use case these days of the speech recognition problem, and that is speech to speech translation. So that is when you have somebody speaking in one language, say Hindi, and you want to be able to communicate with somebody who speaks some other language, say Kannada. So you have a speech recognition system that's going to first recognize the Hindi speech and transcribe it. And then you're going to have a machine translation system that will translate from the Hindi transcription to, Kannada. And then you have a text to speech system that will speak out the Kannada and produce speech. So the other person on the other end can actually understand it. So that's the traditional pipeline for speech to speech translation. And so this is another nice new application for speech recognition. So when we talk about trying to build machine learning solutions for things, the obvious question is, what are we trying to optimize for? How do we actually evaluate these speech recognition systems, and how do we know how good they are? So there are a bunch of metrics that people have proposed, but really there's only one metric that is used, is very popular, and we'll be focusing only on that one. So the catch is that if you want to evaluate how good the speech recognition system is, so basically the recognition system is going to take some speech and produce some transcript. You need to have reference transcripts for that. And those reference transcripts are typically done by human beings. So some human being, one or multiple human beings, will sit and listen to that speech and then write down what they hear. And then the machine will try to recognize that speech. And then you compare those two and see how close the machine is to what the human beings thought. So these are reference transcripts, and you need these for all the sentences in your test set that you're trying to evaluate it for. So the metric that's really used is called the word error rate, and it's basically the number of insertions, substitutions, and deletions divided by the number of words in your reference transcript. So if we look at a couple of examples, so suppose what the speech says is really, it says what a day, and your speech recognition system has hypothesized that there is an extra word there. It thinks you said what a bright day. And so your word error rate is now, so you have basically one insertion. So you have, 1 divided by 3 into 100. So that's 33%, 33.3%. Then there's substitution where, instead of hearing bright, it heard light. And now your word error rate is 25%. And then there's deletion, where you just delete, where the speech recognition system basically misses out on a word. So then again, the word error rate is this much. So depending on what kinds of errors are made, there is slightly, different weightage on these different kinds of errors. And you can even have word error rates of higher than 100. And so basically, it's not 100% clear what exactly, what's a good word error rate for a general system, but we'll talk about systems that have reached human parity. So they've basically become as good as human beings at transcribing speech. So this is a metric that we're going to use throughout the talk, and this is the standard metric. And we're going to compare what the word error rate was for different systems from the beginning, not beginning, but from very long ago, when speech recognition research was going on many years ago, to now. And we'll see what changes were there. So we're really looking at progress in speech recognition based on the word error rate metric. So here's a nice graphic, and this is basically the progress in speech recognition. The last few years are not marked there, but I've put a couple of points there. This basically shows what research was going on and also what the results were like. So the x-axis is the years, and the y-axis is the word error rate. So it goes from 1 to 100. Note that it's not, it's like the 1 to 100 it's like a log scale kind of thing. So let's look at the left-hand side, the black colored lines. So the black colored lines are read speech. So that's when someone is reading and you're trying to recognize that speech. And you can imagine intuitively that when someone is reading, they're reading much more carefully. They're articulating their words much more carefully. So it may be easier for a speech recognition system to actually recognize that. There may not be as many variations as there are. And also when it comes to things like conversations, people do a lot of false starts. So, like I'm speaking right now that way. So I have a lot of knows and and so on. And people don't typically do that when they're reading. So all those things confuse speech recognition systems. So read speech is typically easier. So that's what the task was when they started. And you can see that they started way back in 1988. Um, there's another dimension to this, and that is the vocabulary size. So the vocabulary size is basically, you can think of it as the number of classes that you're trying to recognize. So the number of words that you're actually able to recognize, your system is able to recognize. And they started off with a very small vocabulary, so that's just 1,000 words. So you can only recognize these 1,000 words. Anything outside these you cannot recognize. Either you mark it as you don't know what it is, or you just recognize some other word instead of that. So you can see that when they started this out with 1,000 words, the word error rate was pretty good. It was around, say, 20% or something like that. And within a year or so, the word error rate came down to less than 10%. So we were doing pretty well on read speech already. And this was way back in the 80s. Then they decided to increase the complexity a little. They did the 5,000 and 20,000 tasks. And you can see that, initially the results were not great. They were quite high, the word error rates. But then after a couple of years of work on that also, they could bring down the error rates of the 5K to much less than 10% and of the 20K to around 10% or so. There were a couple of other conditions also for the read speech. So all the black stuff is read speech. So one of them is the noisy condition, where it's, one of them is the poor microphones condition. So the noisy and the clean are where the microphones are not great. Those things also add to the difficulty that speech recognition systems have. So in the noisy case, the word error rate was higher. And in the clean case, again, they brought it down to less than 10%. Even for 20K. So you can see that by 96 or so, we were pretty good at doing, read speech, less than 10% word error rate, which is quite usable. Next, we look at the blue one, which is broadcast speech. So broadcast speech is something like, actually something like newsreader speech. And again, this is, easier than conversational speech, but maybe harder than someone actually sitting in a quiet room and reading things. So in the broadcast speech, you can see that it started at a pretty high, maybe 20, 25, something like that, or even higher, 30% word error rate. And then it went down, and by 2003 or so, it was again around 10% word error rate. Let's look at conversational speech now. So conversational speech started way back in 92 or 93. And you can see that the word error rate is almost 100%. And this is not very surprising, because conversational speech is really the hardest kind of speech to recognize. And especially when it's very informal, you may have observed that yourself. When you talk, when it's extremely informal, you use all kinds of words which are really hard to recognize as real words. They're half words or false starts or other kinds of things. So after that, there was some improvement. So if we look at the 2000 or so, we're still at around 20% word error rate or so. And there's one interesting corpus that was called switchboard. And this is the corpus that we're going to talk about for the rest of the talk. This is basically people calling each other and talking to each other. And so it's conversational speech on the phone. And this switchboard, when the task started, the error rate was around 23% or so. And that's when sort of this chart gets that's when it stops, and then I put in some data points. So after 2003 or so, you can see that there was this 2012 system which went around 10-12% word error rate. And then in 2016, we had a system by Microsoft which went to 6.3% word error rate. And then very recently, in late 2016, the human parity system came about. So that was a slight tweak on the 2016 system that I talked about. So that had 5.9% word error rate. And why is this, great? I mean, why is this so interesting? That's because human beings are not 100% accurate at transcribing speech either. They don't hear all of it accurately. So human beings also apparently have a 5.9% word error rate, and this system matched human beings at the word error rate. So it was called the human parity system, and this is on conversational speech, which is considered to be the hardest kind of speech to recognize. And the fact that we could get here was a very big achievement. And it made the press. There was a lot of news about it and all that. And this is this was made possible because of deep learning. So if you see, from 2003 onwards, there were quite big jumps in the conversational speech problem. And that was all because of deep learning. And so that's what we're going to sort of talk about. We'll talk about what happened before, what the machine learning algorithms were, and what happened after, and then what exactly is happening in these systems, at least what the architectures are like. And then also one thing to remember, which you may not immediately think about, is that all of this was done on the switchboard corpus. So these numbers that I'm talking about, the 6.3 and the 5.9 and so on, are all on switchboard. And uh, yeah, so sorry, if you have any questions, I think you'll have to ask Jacob, and he'll be able to tell you, he'll be able to convey it to me, I think. And I don't know exactly how that's going to work. So, okay, so I have a question here. So, error rate is minimized by gradient descent. Yeah, error rate could be minimized by gradient descent. I mean, it depends on what the architecture is, but that's what you're trying to optimize for. So, yes. Broadcast speech recognition accounts for background music or noise. It depends on what kind of corpus it is. It may account for some background noise, but it really varies from corpus to corpus. So it depends. But ideally, yes, it should be able to deal with some noise. Okay, so if you have any more questions, please tell Jacob. He's going to message them to me, and then I'll try to answer them as the talk goes on. And then we'll keep some time in the end also for questions. Yes, so I was saying, sorry, before I lost my train of thought, that the switchboard corpus is an English corpus, and it's been studied very, very widely for so many years. So they're really good at solving this particular switchboard task. So this doesn't mean that all of speech recognition is solved, or all of even English speech recognition is solved. And we'll talk about what is not solved in a bit. So let's talk about the simplest speech recognition approach. This is called a template-based approach. It's very simple, and it's basically where you have two pieces of speech and you want to compare them, and you want to say whether one of them is similar to the other or not. And basically, you can think of the use case for this as some sort of toy that you can talk to, and you can tell it, say, 5 things or 10 things, and it will do those things. So say it's a talking dog or something. I mean, a dog that can listen to your commands or something like that. You can tell it to do certain things, it'll do them. And there are very fixed things that you can say to it. So the system already knows in advance what it is expecting, and it's not going to attempt to recognize anything beyond that. So in that case, it makes sense to have some sort of templates for all of the things that you're trying to recognize, and then match all incoming speech with those templates. So that's how template-based approaches work. This is good when you have low vocabulary, so less things that you want to recognize, and also closed. So when you know what the things are that you're recognizing, and you don't expect anything outside of it. One of the details in this is that when we speak, we don't speak at the same rate. So you may have stored a template that says something, but somebody else may say it much faster. So you use this technique called dynamic time warping, and basically you use that to align two pieces of speech together, and then you use various features from those, and then you measure the distance between those. So that's how template-based approaches work, very simple and intuitive. Now, one of the things that was sort of standard for many, many years in speech recognition, and even today it's used, but that's one of the things that deep learning changed quite a bit, is that you did feature extraction from the audio, which you know that very well, being interested in deep learning, that the real power of deep learning is the fact that it can actually learn representations of data. So before that, this representation was extracted through a specific feature. And this feature is called the MFCC, or the Mel Frequency Capture Coefficient. There were other features also that were proposed for speech recognition, but this was one of the standard ones. So it's supposed to be perceptually motivated. Basically, what you do is you take the signal, you divide it into frames, you get the power spectrum, you apply these MEL filters, which are specific filters, and then you do some other things. You take the log, you take the DCT, and so on. Basically, at the end of it, for each frame, so each frame is 100 200 milliseconds frame, and you get 26 coefficients for each of these frames. And with these are your features, basically, these 26 coefficients. And usually 12 of these are used for ASR. So this also varies a little bit, but you can think of some of these coefficients being useful for doing speech recognition. So these are the features you actually extract from the signal. And as I said, many other features were also proposed. So this is just basic background about what features were used. Now I'll talk about the systems that were used for a long time, which were standard till the DNN thing. So you can think of it as doing two different things for speech recognition. One is trying to recognize what sounds the signal has, and the other is trying to actually recognize what words are there in the utterance. So for recognizing the sounds, you typically use the waveform and you try to figure out what sounds are there. But you can also use some knowledge that you have from the language itself, and that's called language modeling. So you know that some sentences in English are much more likely to occur. Some words are much more likely to occur together than other words, and you use that knowledge in actually figuring out what the utterance that was there in the speech is. So I'll show you how that works. So suppose you have a sentence like this: recognize beach. Now you know that recognize beach actually sounds a lot like recognize speech. And if you know how English works, you know that the phrase recognize speech is much more likely than recognize speech, even though the sounds are very similar to each other. So you can use that and actually sort of re-rank your hypothesis and say, no, recognized speech is much more likely to occur than recognized speech. So this is something where you sort of divide the problem into two parts. One is the acoustic modeling, where you try to figure out what sounds are there, and the other is taking help of knowledge you have from the language to do language modeling. So acoustic models are, some of the stuff I'm going to say in the next couple of slides are a little sort of hand wavy because I'm not going to too many details, but I'm purposely not doing that because I don't want to go into those many details here. So the acoustic models you can think of as the probability of the phones given the sounds, and the language models you can think of as the probability of the word sequence. So basically your task in speech recognition is to find the probability of the word sequence given the observations. So the observations here are the actual speech. So you can write it down as P of W given O, and because of Bayes' rule, you can flip this around and make it P of O given W into P of W upon P of O. So we can ignore the denominator because we want the maximum. So P of O given W is basically the acoustic model. So what's the probability of the observation? So the speech given those Ws, and P of W is your language model. So this is how you formulate in the old setup the speech recognition problem. So for training the acoustic model, you basically need lots and lots of speech, and you need the corresponding label. So you need to know what sounds were there at what points in the speech signal. And for building the language model, you basically need lots of words. So you need a huge text corpus. And with that text corpus, you can do various language modeling techniques, so n-grams being the most popular one. So the acoustic models were typically built using hidden Markov models, which are like a time series kind of thing. So given speech, you try and figure out what sound it corresponds to. And what happens is that, so basically I should say this, that in speech recognition, speech synthesis and so on, I mean, in general, the basic unit of sound is called a phone or a phoneme. And you can think of each language having, say, between 20 or 30 to, say, 50 or 60 or even more, maybe, sounds in them. So your acoustic model is basically trying to build a model for each of these sounds. And so how many models do you need? Suppose your language has 50 sounds. So are 50 models enough, one for each sound? Turns out that that's not the ideal way to do it because sounds are different depending on the context. So typically you do something like triphone models where you model the phone before and after as well. So you have 50 raised to 3 models. But of course, since there are so many models, you need lots of data to train each of these models. And so there are some techniques to actually sort of bring down this and so on. Each of these states is a GMM. For language models, you're basically trying to figure out the probability of the word sequences. And there are multiple ways of doing this. So there are grammars, there are n-gram language models. N-gram language models are the ones which are most common usually. And n-gram basically means that, say trigram means like there are three. So what's the probability of finding these three in a sequence? So the way you estimate this is you take a very large corpus and you calculate the counts, and then you try to figure out the probability of this word appearing after this word and the previous word and so on. And then you figure out what the probability is based on that. If you don't have that context in your corpus, then you can also do back off, which is basically if you don't have a word following another word, then you can back off to a bigram or a unigram model. There's also some smoothing that you do. So you don't want probabilities to be zero if the word doesn't occur in that context in your corpus. So you do some smoothing to make sure that they aren't zero, but they are some small number. There may also be out of vocabulary words. So in this case, you can choose what to do. So your speech recognition system can only recognize a fixed number of words. So any word that you think is not one of those, you can mark it as out of vocabulary and you can say that you don't know how to recognize it, or you can try to somehow figure out what the transcription for that should be. So there are techniques to do both of them. So if we put all this together, so this is the old setup, remember. So you have the acoustic model, so basically gives you what phoneme it is given the acoustic. You have the language model, which gives you what the word sequence is. So recognized speech is more likely than this, for example. Now there's this other thing called the pronunciation dictionary, which basically takes each word that you have in your language and gives you what the pronunciation is of that word in terms of sounds. So you need this to basically map from the language model to the acoustic model. So this is sort of in between the two. And this is also really important because remember that all of these are resources that you need to create to be able to do speech recognition in any language. So you have to actually have enough data to train the acoustic model. So you need speech data and you need the transcript for that. You need enough text data to be able to train the language model. So you need lots of text in that language. And you need this pronunciation dictionary. So you need somebody or something to come up with the pronunciation of every single word that you have in your language that you're expecting to recognize. And, so this is how that's going to look. All this comes together, and then there's a Viterbi search over the entire space. There are all sorts of things to make it more efficient, pruning, beam search, and all those. So putting all of this together with the old setup with the acoustic model, HMM-based acoustic model, and the, say, n-gram-based language model, and this kind of pronunciation dictionary, and so on, the word error rate for the switchboard corpus that we talked about was 23%. So this is what we have to remember, like this 23% number. This is what we're going to compare the rest of the results with. So what do you need? So I must say that I did my PhD in speech synthesis for low resource languages. So I'm really interested in actually building up these speech systems for the non-English, non-Chinese, maybe first top European languages. I want to do it for languages beyond just those, because I think that those are the communities that really need speech systems, especially languages that don't have a written form. Those really need speech systems to be able to communicate and so on. So what does it take to actually build this ASR for a specific language? So you need lots of transcribed speech for the acoustic model. And this turns out to be around hundreds of thousands of hours in commercial systems. So you need this much speech, and you need somebody to actually sit and transcribe all of this by hand. That's how you're going to train your speech recognition system. So that's what you need. For the language model, you need lots of text. So this turns out to be around millions of sentences in commercial systems. So again, you need millions of sentences in your language. And this may be non-trivial to obtain because even though, online there's lots and lots of text, it may not be there for your language. It may not be in the format that you want. It may be in some weird font. It may not be in UTF and so on. So it may be non-trivial to actually get. So for example, for many of the Indian languages, we find that it's quite hard to get a lot of text online, because when we write, when we type in Indian languages, we tend to Romanize things and type them in Roman alphabet and not in the native alphabet, so native script. Yeah, so I have another question which says data set that I mentioned, switchport, is it available for public use? I think it is available for research use. I'm not 100% sure, because I haven't ever worked with it, but I'm pretty sure it is available for research use. I may be wrong. I can check. But if you just Google switchboard, you should be able to get it. It's a very, very popular corpus. All right. So that's what you need for the language model. The other thing with the language model is that you need to keep updating the language model as new words come into the language. So if you're expecting that the language evolves very quickly, which it does these days, you need to keep updating your language model. And if you're training this huge, huge model and it's going to take days and days to train, and then you have this new word that you want to introduce, it may not be that easy to actually do it so that's a non-trivial thing. And then for the pronunciation dictionary, you need the pronunciation of every word that the ASR system expects to recognize, as I said before. So no wonder building ASR systems for new languages is quite hard. And one of the major problems is data, because the rest of it can be, to a certain extent, automated using machine learning now. But you still need lots of data, and getting that data is not easy. Especially speech data is not very easy to get. All right. So, are there better ways of doing this other than this acoustic model, language model, dictionary kind of approach? Is there something better? Can it be used for these low resource languages? Or do we still need to depend on lots of data? So, we'll just take a look at that. So, okay, let's start with the actual stuff that you're interested in, the deep learning stuff. So, there was a, paper that came out, which was a pretty unique paper, I think. So written by Hinton, and there's people from MSR, and there's people from Google, and there's people from IBM on a single paper. So you can imagine. And this was called Deep Neural Networks for Acoustic Modeling and Speech Recognition. And this was really, one of the first papers that talked about how we could use deep learning for speech recognition. And the authors also say that this was really a consolidated effort between all these research labs and Hinton. And that's why they could actually do this. And this is what really started things. So what do you do? So first you take the MFCCs. So those are the features that I talked about, the Mel frequency cepstral coefficient features. And you take the GMMs, HMM, and you replace those. So instead of GMM, HMM, FCC, you have now DNN HMMs. And DNN HMMs are the ones which are going to do your feature extraction for you. And the HMM is still going to model it, but now you're not using these MFCCs anymore, because as you all know, DNNs are really good at data representation. So instead of using hand-engineered features, you use the DNNs, you use these raw spectral features. Then you use the HMM as before to model them. And this alone gave rise to a reduction of 10% absolute in the word error rate. So from 23%, it went down to 13%. And this is really the biggest jump that speech recognition had. And it's not very surprising, given similar things we have seen in image processing and so on, where representation is really the thing that DNNs are good at. So even with this architecture, you still need the HMMs, you still need the pronunciation dictionaries, you still need the language models and all. So even though the word error rate has gone down a lot, the resource requirement is still pretty much the same. And so, at least from people who want to do other languages point of view, it doesn't really solve the problem that much yet. But it's still pretty good. So I was at the ICAST conference, which is the International Conference on Acoustics, Speech and Signal Processing. Yeah, that was in 2013. And that's when I actually saw, DNNs be really, really big in speech. I'm sure they were even before that, but this was the year that I noticed that there were keynotes and lots of sessions and so on deep learning. And I was pretty surprised about that. All right. So that was sort of on the acoustic modeling side, even though it's actually really the front end, the feature extraction part. Now, what about language modeling? So anyone who's worked with language models for other things. So language models are also used in machine translation and other applications. So they're not just a speech recognition thing. You know that people have been replacing these n-gram-based models with the recurrent neural-based models. And why is that? So the problem with n-grams is that you have a small history. So if you want, if you want to do 3 gram or trigram or something, it's okay. But if you increase that to a 4 gram or a 5 gram or more than that, then you need lots of data. So you have lots of parameters, you need a lot of data, and it becomes very complex. So you typically don't do that. So if you only have a trigram context, then you can't really look back in history that much. The other problem is with n-grams, each word is treated completely differently. And you know, right, that similar words probably share similar histories. And so there should be some way of sharing this information, but there isn't in the n-gram setup. So the solution to this is to project the history into some low dimensional space. So word embedding, similar words are near each other, parameters are shared, and so on. We know all of this. And first they tried to do some feed-forward network-based things for language modeling, and then recurrent neural networks really became the standard for language modeling. So the way it works, of course, is to project the entire history into a low-dimensional space, and then you have this short-term memory and so on. So word error rate-wise, it was not a huge improvement. The recurrent neural networks, it was a 1% improvement. But even then, so when you've got down to 13% word error rate, even a 1% error rate is a very big improvement. And again, this is on this specific task. It may be different for different tasks, but even then, this was a very encouraging sign that recurrent neural networks were actually doing like 1% better. The only problem is that these are really slow. So they were not directly used for decoding while doing like live speech recognition, but they were used for rescoring lattices. So not directly integrated into the system, but used for rescoring. Okay, now I have a slight detour from the general DNN setup and talk about one more interesting thing from my point of view, since I work on multilingual systems. Um, so you've heard about the zero shot empty kind of stuff from Google. So this is actually similar for ASR. So far, what we were doing was we were training different models for different languages. So if you want to do English ASR, you take English corpus and you take, all that, you build your system and then it does English. And if you want to do Hindi, you do it for Hindi separately and so on. But what some people said was that these hidden layers that are there in these DNN based systems, they may actually capture language independent features. And since these are language independent, we could actually reuse them across languages. We could share this, and that may help in the data scarcity or whatever, those kinds of problems that may be there for low resource languages. So the idea is to share these layers amongst different languages. And so the way this works, I'm not going into the technical details of it. There is a paper, if anyone is interested, I can point you to that. The way you do it is you train the DNN with all the language data. So suppose you're doing Hindi, English, Kannada, and some other thing. You train this with everything, and you have language specific weights in the first layer. And to decode one specific language's speech, you basically throw away the first layer and you train the first layer and the connections using that language's speech only. And that way you can actually use that network to decode that particular language's speech. So one of the experiments that was done, so I haven't put a citation here, I should, but I can, when I edit the slides, I can put that in for this paper. So the way it did it was it took French, German, Spanish, and Italian and trained the DNN on all of this. And then it used this to decode French. Now, if it turned out that the multilingual stuff didn't help, then the word error rate for decoding French should have been the same whether you train it with only French or whether you train it with French and German and Spanish and Italian, all of them, right? But it turns out that this multilingual system is a 3.5 word error rate improvement compared to the French only system. So which means that there's actually some sort of improvement happening by doing this whole multilingual training. It's also true that the amount of data is more if you combine all of these languages, but it's not just, it's not, the data is not in the same language, it's in some other language. So which means that, the multilingual thing is actually working quite a bit. So this is a pretty cool sign. So this means that if you want to do low resource languages, you may be able to take some high resource language like English or even Hindi. If you take Hindi as a high resource language and you want to do say Marathi speech recognition, then what if you build one DNN for Hindi and Marathi and some other Gujarati or something like that, and then you want to recognize only Marathi from that. So you take that away and then do a monolingual Marathi, and then maybe that will be better than just training it on only Marathi data. So experiments haven't been done to verify all this to a large extent, but it looks like an interesting idea that could have some potential. So this is something I'm excited about. Now I'll talk about the 2016 DNN-based system. So just give you what it looked like. And this was the one which had 6.9%, or is, I think this 6.9% word error rate. And some tweaks to this actually brought it down to 5.9, which was the human parity system. So this system is actually an ensemble system. It has CNN and LSTM both. Uh, the CNN expands the window size layer by layer, and then there are attention masks for important content. The language model is an n-gram model, and it first produces these lattices, and then RNNLMs rescore these lattices. So there's basically forward and backward RNNLM that does the rescoring. Again, there is a paper on this, which I should cite, which will have all the details of the exact architecture and experiments. So so this is the same language model, and this caused a 1% word error rate difference. There's also something they did to speed up the training. So one of the things that the MSR people said was that uh, the the thing that is there in CNTK, the cognitive toolkit, I don't know how many of you have tried it out. It's called 1-bit SGD, and this apparently speeds up training quite a bit. And because of this speed up, they could build these models quickly and try lots of different architectures. And that was one of the reasons why the human parity thing actually happened, because they could try a lot of things very quickly because of this very big speed up that they got in CNTK. Now, another very interesting system that has come is the end-to-end system. So, so far, even in the MSR 2016 system, you're still using all those resources like a language model and a pronunciation dictionary and so on. You're not getting away from that. And if you want to do it for a language that doesn't have all those resources, what do you do? So the end-to-end ASR system is actually one of the solutions to that. So this is based on CTC in RNN. So CTC is the connectionist temporal classification, I think, that technique. And yeah, so as I said, the earlier DNN systems, the current DNN systems are still using language models and pronunciation dictionaries. And so now this is a technique to map directly from the acoustics to the symbols, which are the words or the letters in this case. So this is very similar to a lot of other, you've seen this in many other applications also, like TTS and so on. So basically you take the audio, you take the thing that you're trying to predict, the letters or the words, and then you just let the DNN figure out the entire thing in between. So in this case, it's a letter-based decoding. So when you do speech recognition, you're not recognizing words, but you're recognizing letters. And one of the things that happens in these systems is that the output that it gives you is not exactly, it may not make sense because it's not giving you at a word level, but only letter level. So there's a system that actually takes that and then converts that into meaningful words. So there's a second network that does that. So it improves the noisy decoding. And this whole setup gave rise to 17% word error rate for switchboard. So remember that this is using only a DNN system from the acoustics to the words or the letters in this case, and no language model, no pronunciation dictionary, nothing. And this itself gives a 17% word error rate, which is not bad at all, considering that the HMM based and the Ngram language model based system gives you 23%. So this is actually better than that, and yet you're not using all those resources that the current system is using. So we're not at the human parity thing yet with this technique, but we're not very bad either. So I think this is very promising, and especially for languages that don't have all these resources, even something which gives you 17% word error rate, I think is pretty good and maybe usable. So yeah, so there was another tweak also to this where they used a word-based RNNLM and they got even lower, 10.2% word error rate, which is really good. So almost going to end now. Took a little longer than I thought. So what are the things? So I've basically given you an overview of what speech recognition is, what the problem is, what the earlier solutions, machine learning solutions were, what's happening in DNN, and what really the big things were in DNNs that changed the field. And going forward, is from my biased view of being interested in multilingual systems, what's there. So I think that multilingual training, where you train the system on lots of languages and then you decode one language. I think that's very cool, and it has potential for the languages that are not typically considered the low resource languages. This kind of thing is also being used in speech synthesis and in other fields. So the zero shot learning is one of the machine translation stuff is one of them. And end-to-end models also are very cool, I think, again, because they get rid of the resource requirements, some of the resources at least. And again, these kinds of things are being explored in lots of other fields as well. So I'm going to stop there, and I'll be happy to take any questions. So I'm assuming that you can continue asking questions to Jacob, and then he'll send them to me, and then I'll try to answer them. Okay, so one of the questions is, where are we today in terms of Indian language ASR? And I think it depends. I think there are some great companies that are working on, specifically working on Indian language ASR. I haven't seen any open systems in research that are really, like large scale systems that are very robust and so on in any of the Indian languages. There used to be some for Hindi, but I haven't seen them for any of the other Indian languages. So yeah, but there are companies that supposedly have built speech recognition systems for a lot of different languages. The problem is also that unless there is some standardized data set, like say switchboard or something like that for Indian languages, it's very hard to compare, word error rates. So if someone says, "Oh, I have a 10% word error rate on, Kannada or something," but then their task is very simple, like read speech or something like that, then you can't really compare that to, somebody else who has a 30% word error rate on conversational speech. So very hard to do that without standardized data sets to compare, and that I don't think we have any for the Indian languages. Okay, so I have another question which says, switchboard is not available for public use. Can you suggest any other data sets? So I think, the only data sets I've really played around with are LDC ones. So LDC has a bunch of data sets. I think there is some data on some other, like there are specific websites that have a lot of speech data. So Voxforge, I think, is one of them. I'm not 100% sure. It's been a while since I actually got non-research data, so I'm not sure. But I think if you search around, you should be able to get something. But if you're specifically looking for some languages, it'll be much easier to get English language data and much harder to get non-English data. So if you can get hold of LDC data, that is best, I think. Okay. So somebody else, so also the TIMIT, so TIMIT is a good corpus as well. You can definitely try building systems on that, and there are a lot of numbers also for TIMIT. Somebody asked, Jacob asked, what is the state of the art architecture for ASR? It's changing very rapidly. So when I made these slides to give a talk somewhere else, that was in late last year. So the all neural end-to-end thing was the, sort of the in thing at that time. But the 2016 system, the CNN LSTM acoustic model system with the RNNLM for rescoring, that is the state of the art as far as the Microsoft system goes, and that's the one which has human parity. So that's the one I know of, but I don't know exactly what the Baidu system architecture is, but I'm guessing it must be similar. So I think CNNs have become popular recently for speech recognition. It used to be really LSTMs and things like that, but CNNs recently have become very popular for ASR. Someone asked, any connection between never-ending language learning and speech recognition? I don't think there is any connection. So as far as I know, the NEL project is basically trying to get hold of concepts, trying to learn concepts automatically by reading the web. So there is no connection to speech recognition. Okay, so those are the questions. Anything else before we end? And yeah, I can, just very briefly talk about the actual research I do. So I work on code switching, and our entire team in Microsoft actually does that. We are a group, quite a large group actually now. So especially in multilingual societies, you see that a lot in India. There's, people, when they talk to each other, especially when they're having casual conversations, they don't talk in a single language. They switch between languages a lot. And this is called code switching or code mixing. And this is something that current systems are not able to handle. And so if you imagine some sort of agent that has to recognize your speech in India, you would really want it to be able to recognize अरे क्या time है, अरे मुझे यहाँ जाना है, or something which has multiple languages in it. And we do that very effortlessly and seamlessly without even realizing it. But most of these systems cannot deal with it at all. So that's what my research is on, and that's what I work on. Okay, any open source tools for pre-processing raw speech corpus, FFT? And yes, there are a lot of them. There are a lot of tools in multiple packages. So I know that there are lots of MATLAB kind of packages. There are also specific signal processing toolkits and so on. If you have any real specific questions, you can feel free to email me. So my email address was there at the beginning. Let me bring up that slide, because I may not be able to tell you off the top of my head what corpora and things and toolkits are there, but if I search a little, I'll be able to. Yeah, so also, if you're interested in speech recognition and you're interested in doing internships and things like that, feel free to apply at MSR uh, or get in touch with me directly. Okay, I guess that's the end of the questions. Okay, cool. So that's the end of the question. So thanks so much for being on air if you're listening to this live. And it's great that I'm really enjoying reading all the posts on the IDLI group and participating. And if there are any women out there, please participate more and you know participate in the discussions and so on. So yeah, so maybe after a few months, I'll give an updated talk about my actual research when it's a little further along. And if you have any other specific questions, please feel free to get in touch with me or email, and I'll be happy to answer. Thank you so much for listening. Bye-bye.